the goal of this video is to get us a little bit more familiar with graphing polar functions. And one of the goals also is to be able to become less dependent on a graphing calculator to know the behavior of certain functions. And some of those functions we're going to look at, we've seen before, some of the relationships we've seen before, like circles and ellipses and conic sections. We will now view them through the lens of polar graphing and be able to represent them as functions, which was really a big idea we've already seen. But then also there are other characteristic functions that we associate with polar graphing. And, those characteristic shapes often come up on the AP exam next year in calculus. So, we want to make sure that we're prepared and get a good foundation this year as we start looking at those kinds of relationships. Now, one of the first ones we're going to do is something called a polar rose. And a polar rose is based on sine and cosine. So it's really appropriate, I think, right, for us to study this in trig. And, you start manipulating sines and cosine graphs by changing their amplitude and changing their frequency, which is like their period of the wavelength. But the shape, because of the way we graph things in the world of polars, is going to look quite different than the sine graphs and cosine graphs that we're used to. I want to show on both your graphing calculator how to switch into that mode, but also show on Desmos, if you wanted to explore a few things as we start looking for these patterns, right? So as we start looking for these relationships. So in your graphing calculator, so I've got a website pulled up here that to simulate the graphing calculator. So if you're just from your home screen, whatever you've done, go ahead and go to mode, which is right there on the top, and right below where it says radians versus degrees, there's a way to shift your calculator from functions to parametrics, which we'll look at next chapter, polar or sequences, like if you're doing like sequences in series. Arrow over to where it says polar, hit enter, and I'm going to throw myself in radian mode too. So if you are in degree mode still, go back to radian. Okay, so if you hit quit, you can go to your home screen, nothing's going to look different. But it's all of a sudden, if you hit y equals, now you've got a bunch of r's, right? R equals this, R equals that, R equals that. And, that's because we want to start graphing r in terms of theta. And just so we all have the same viewing window as well, my window right now says what's your minimum theta and what's your maximum theta, and it's 0 to, well, this decimal is actually 2 pi. Since I'm in radians, 2 pi makes sense to go for our window, right? Now, a theta step, I think the generic theta step is like about 0.13, and what that theta step is, and we'll adjust that. It basically is it's how often will your calculator evaluate an angle and then basically connect the dots. Now, in terms of my x min and x max, like I can go from like -5, let's say, to +5 with a scale of 1. And then my y min -5 to +5. So even though we're graphing r in terms of theta, you still have a window of x and y, and how much is it opening left and right, up and down. Okay. Now, when I go into y equals, and I want to start looking at maybe plotting a polar rose. A polar rose has a coefficient in front, like an amplitude, and you can pick either sine or cosine. And then it needs a frequency to change its wavelength. So maybe I'll pick a 3, and then you pick an x. But the thing is since we've moved into the polar mode, the calculator, when you hit the variable x, it already knows it should be in theta. So that's really nice. And then in fact, the order, if you've ever noticed the xt theta n, that's because it follows the order of your calculator. X being function, t being parametric, because time would be our variable that we're going to study. Theta in polars is our variable, and n is the variable when you go into sequences and series. So if I hit graph, I get that picture. 3 petals, right, or 3, which are called petals, like these 3 regions. And it went pretty quick. And it's a bit skewed because our graphing calculator is longer left to right than it is like up to down. So if you want to adjust it to make it appear relative scale-wise, so it looks like it's not been stretched. There is a function under zoom. It's called zoom squared, and you could use this in any mode. But if I zoom square this, it's like it gives me a little bit better of a perspective. And then if that went too fast, so go back to your window, and if you change your theta step to like 0.01, 0.03089996, whatever that value is. And now when I hit graph, it's going to go a little bit slower because it's graphing more points at a time. Now I'm also seeing some overlap here that I didn't see the first time. And that's going to be important, and we're going to start looking at why that's happening. Now, if for some reason you're not getting much of a graph, it's probably because you're in degree mode, and going 0 to 6 degrees is a lot smaller than going from 0 to 6 radians, which is about 2 pi. So make sure you check your mode. Okay, so at this point, you should kind of like play around with this a little bit. Like instead of a 4, what if you made that a 5? Right? What's happening to our graph? I still have the same number of petals, but I don't know if you've noticed the petals actually grew, right? Because of that amplitude. So, if you make that a 6, the petals are growing bigger. So just like in a normal sine and cosine, when that lead coefficient deals with amplitude, the length of the petal is sort of like the amplitude, in the world of polars. And you could, switch out cosine. What does it look like if you put a sine function there? And again, the idea is for you to start playing around with these two values, like the A and B, what's happening. And we've already sort of talked about A, right, is affecting the amplitude. Start playing around with your B values, really, as long as you keep them whole numbers, don't make them decimals, because that loses the characteristic shape of a rows. You get a different graph, but you need to be responsible for what happens when they are, coefficient or like just whole numbers. So we've seen 3, and we had 3 petals, and so you might argue, or you might estimate that if there's a 2, there'd be 2 petals. But as we can see, we get actually 4. And is that pretty, like a little butterfly? Or like, again, the idea is that they almost look like petals of a flower. Now they're called roses, polar roses, but it sort of looks more like maybe a daisy. And so then you might start wondering, well, okay, 2 theta gave me 4 petals, and 3 theta gave me just 3. So I wonder how many 4 would give, right? And you can graph, and we can start seeing there's 1, there's 2, and look at the order that it's graphing to, by the way. Oh, this is very pretty. Look, there's 8, right? And again, as you kind of think of your characteristic daisy-shaped flower. Now, I changed my amplitude. I changed my amplitude to a 6. So if I make that more of a 5, I'm going to be able to get all the petals in there. And so again, the way this calculator is graphing, it's kind of going in and out of the origin, right, or in and out of the pole, and that's going to be important too. That's a very nice flower. And even if you switch that from sine to cosine, you're going to notice that you're going to get the same number of petals that you had sine. It's just it's starting in a different spot. So that's pretty cool. You maybe have this conjecture that, okay, well, if 2 gave us 4 petals and 3 gives us 3 petals, 4 gives us 8 petals, how many is 5 going to give us? We're going to see that 5 gives us 5. And even though it's overlapping here, there are 5 distinct petals. I don't know if you caught that this up here in the upper right, it was still thinking, it was still graphing, even though our image really didn't change. So it appears to be when we have these odd numbers, so if I change it to a 7, I'm going to see 7 distinct petals. Even though the calculator is going to continue to graph and do some overlap, there are 7 distinct petals. And so really the parity, is it even versus is it odd, is really, really important. Now I skipped 6. 6 is even, so I'm going to be able to see doubled 6, or I'm going to see 12 different petals. So that's pretty cool. Now, like I mentioned, I said I'd show this on your graphing calculator. You could also go into Desmos, and so for Desmos, I've got a whole bunch of things graphed here. But if you want to program something or type something in Desmos, first of all, you have to make sure you go into under your grid. There's your rectangular grid, there's your polar grid. So that's how you're gonna throw it into that polar format. You could label radians, you could label degrees for your coordinate system. But in order for Desmos to graph polar, you have to type in r equals, and then let's say 5 sine, and then to get the character theta, you actually have to type in the Greek spelling theta, so T-H-A-E-T-A, and then it throws in the theta. So maybe you want 5 sine of 5 theta, right? And so 5 sine of 5 theta. So now, again, it's a little bit more better perspective. I'm thinking of Patrick Star from SpongeBob, right? But 5 as our coefficient, 5 petals. And if I change it to a 4, I see 8 petals. If I change it to a 3, I see 3 petals. What I don't like about Desmos is that you don't get the fluidity or the motion of the graph. You just get the end of it. And so I'm going to show you how you can actually see it graph as it goes, but it does give you a sense real quick of like what the end result is. Like you wanted 7 petals versus 8, right? There's 16. And in fact, what I did up here in this particular function is I made a slider. So k being 1, I get 1 petal, which is a circle. So that's coming up soon. But if I start looking at what happens when I have 2, and then 3, right? And then when k is 4, and again, k is just the coefficient in front of theta, there's 5. 6, we get 12 petals. 7, we only get 7 distinct petals. 8, we get 16 petals. 9, we get just 9 distinct petals. 10, we get 20 petals. 11, oh, it goes back to 9, right? Okay. So I must have put up the cap up to 10. So, so hopefully, kind of playing around with either Desmos or your graphing calculator, we should feel very, very comfortable knowing now what does A represent and what does B represent for these particular polar roses, right? So your coefficient A is going to be the amplitude of your function. In that case, it's going to be the petal length. So A is going to represent your petal length. Sorry, it's so messy. I'm writing it kind of like sideways here to record this, where B is going to represent the number of petals. I should say distinct petals. If you look at when B is odd, so if B is odd, then there are B petals. Then there are, B distinct petals. Distinct petals, okay? When B is even, then you're going to see 2B distinct petals, okay? And, already now, knowing that, if I were asked to graph this by hand, I would know that there'd be 3 distinct petals because of that coefficient 3, and the length of each petal would be 6. In the next video, we're going to start looking at, well, where do these functions start, and how frequently are we going into the origin or into the pole, because ultimately that's going to be the key to graphing these polar functions, like these polar roses. Okay, so again, feel free to play around with as much as you want on your graphing calculator. But the next video, we're going to formalize a method and a procedure based on what's really happening and why is the graph giving us these petals, right? So, okay, excellent.